Okay, so integrating using completing the square. This is going to be the final strategy or method of integration that we're responsible for in this AP calculus course. So this is the final one, and it's closely related to this lesson here when we talked about inverse trig substitutions. So just to quickly recap what the inverse trig substitution lesson was about, it was basically identifying integrals that look like 1 over 1 plus x squared. So we took that and we found this generalized form. If you see integrals of the form 1 over a plus x squared dx, then you can apply that arctan formula. That was the first part of the lesson. The second part of the lesson was to identify integrals that look like 1 over the square root of 1 minus x squared. And so we came up with a generalization for integrals that have this form, the integral of 1 over square root. Okay, so the square root should jump out at you. Some number a squared minus bx squared. When you see that, then you can use the arcsine formula there. Now, today, we are going to be looking at given rational functions with a constant in the numerator. Okay, so if we go back to these inverse trig, these two types of integrals, the arcsine and arctan, they both have a constant in the numerator. Okay, so what I've done here, the first thing I've done here is to break down the three different cases you might have with a constant in the numerator. Okay, so part one. Given a rational function with a constant in the numerator, if you recognize the integrand as the antiderivative of a basic function, then all you need to do is just integrate or find the antiderivative. Okay, so even though the topic is completing the square, we're not using completing the square when you have a constant in the numerator and you can just basically find the antiderivative. So examples, I've got those two examples there, so there's the answer. The integral of 1 over 3x plus 5 is just 1/3 natural log 3x plus 5 plus a constant. There's no magic there. That's just applying the basic derivative rules. Part B, again, we have a rational function with a constant in the numerator. If I take the 3 outside, then I'm left with finding the antiderivative of 1 over 1 plus x squared, which is just tan inverse x. So again, no magic. You just need to know basic antiderivatives for part 1. Or for integrals that are like the ones from part 1. Now, you can also have a rational function with a constant in the numerator where, so this is part 2 now, the integral may require a substitution that will put the integral into something that's more easily integrable. So, this is referring to 2 lessons ago when we did inverse trig substitutions. And so I'll take you through those 2 integrals. Okay, so again, we have a constant in the numerator. But now, we can't just integrate using a simple formula from our sheet. We need to use some kind of substitution. So the first one, A, the integral of 7 over 3 plus 1 plus x squared. It's a rational function with a constant in the numerator. Pull the 7 outside the integral sign, and we get 1 over 3 plus 1 plus x squared. Now we need to use a substitution, because if I let u equal 1 plus x, the integral transforms into 1 over 3 plus u squared, which we know is the tan inverse integral. Okay, we're just applying that formula from the previous lesson. It's 1 over root a tan inverse u over root a plus a constant. Okay, so again, the substitution there was let u equal 1 plus x. When I do a substitution, I find the derivative of u with respect to x, which is just 1, which means that dx is equal to du. So I can replace the dx with du. A is equal to 3, and I get my antiderivative, or I'm done my integral there. Back substitute for u. U is just 1 plus x. The second one, b, again, you have a rational function, or you have a function divided by a function, and the numerator is a constant. In this case, the numerator is a 1. And you recognize that that integral looks like 1 over root a squared minus bx squared, which we know from the previous lesson is just 1 over b sine inverse b divided by ax plus a constant. So we're trying to make that integral look like, because we know when we look at it, just visually, it looks very much like that integral I've written on the right-hand side there. So how do I make it look more like that? Well, I use the substitution. If I let u equal x plus 2, then du by dx, the derivative of x plus 2 is just 1, which means du is equal to dx. So I can replace the dx in my original integral with du. I replace the x plus 2 with u, and I get a simpler integral that looks like what we're after. 1 over root 13 minus u squared. Okay? When I compare it to the integral there on the right, a is just root 13, and b is just 1. And of course, yes, we're using a different variable, but that really doesn't matter. It's the form of the integral. How it looks like is what we're after. So yes, we're using u, but we'll change it back to x at the end. So using that formula there, that integral is just 1 over b. So 1 over 1 is just a 1. Sine inverse b, which is 1, divided by a, which is root 13, times u plus a constant. And your final step is to take that u and back substitute the x plus 2. So I get sine inverse x plus 2 over square root 13. Okay, so case 2, whenever you have a rational function with a constant in the numerator, we can try and make the integral look like the tan inverse integral or the sine inverse integral. Now, if I go back up to the top, there was a third case. If the denominator now, so let's say we have again a function divided by a function and the numerator is a constant, but now we have a non-factorable quadratic in the denominator. And we're going to go through two examples. One of the example has no square root sign, which we're going to try to convert to a arctan integral. And the second one has a square root, has a non-factorable quadratic under the square root sign. So that square root sign should tell you, yeah, maybe we're going to try to convert that to the arc sine integral. And so completing the square is the process that will help us to convert those integrals to the arc sine and arc tan integrals. What do I mean by that? I mean these two integrals right here. I'm just putting asterisks beside them. So how do I do that? So again, now we have to review what is completing the square. How do I do that? Because it's probably been 2 years or more since you've done that, if you've ever done that. Okay, so let's go through these examples. The first one, the integral of 7 over 5x squared minus 30x plus 65. We have a constant in the numerator, and the denominator is a quadratic, which means the highest power is 2, and we cannot factor it. It's non-factorable. So, first step, take the 7 outside the integral sign. Okay? And then you can see on the right-hand side there, I've written complete the square in the denominator. So, to review the completing the square business, write down the denominator, which is 5x squared minus 30x plus 65. Then you're going to look at the first two terms. That's why I've highlighted them there. And I factor out, I see that 5 is divisible into both of those, so I factor a 5 out of the first two highlighted terms to give me 5 times x squared minus 6x plus 65. Now comes the completing the square business. So that second term there, that negative 6x, the way we complete the square is to take 1/2 of that, and you can see I've written on the right hand side in red. Take 1/2 of 6, which is 3, and square it. That gives us 9. Add 9 and subtract 9 to the x squared minus 6x. Close the bracket, and then add the 65 on to the end from the previous step. Then, what I've done there is I've highlighted the x squared minus 6x plus 9. When I factor that, it's just x minus 3 squared. Okay? And I'm left with that negative 9 inside the round bracket, which I need to get it outside of there. I need to multiply it by the 5 in front, which gives me negative 45. And when I add the negative 45 and the 65, I get plus 20. So your second last step of completing the square then is 5 times x minus 3 squared plus 20. Now, if possible, this is not always possible, but in this case, we can factor a 5 out of both of those terms and write the denominator as 5 times, open bracket, x minus 3 squared plus 4. So I'm going to write that in the denominator now. So in the second step there, back on the left, I've taken the 7 outside, and I've replaced the denominator with my completed square form of the denominator. Now, that 5 that's hanging out in front of the denominator, I can take that outside the integral sign. And so I get 7/5 in front of the integral. And now, inside the squared brackets, I've just reversed the order in which I've written them. So instead of writing x minus 3 squared plus 4, I've written 4 plus x minus 3 squared. The reason I've done that is because now it looks like the integral of 1 over a plus x squared. Problem is, it's not just x squared, it's x minus 3 squared. So I've got to do a substitution just like I did in part 2, those two examples in part 2 of this lesson. Okay? So I let u equal x minus 3. du by dx is 1, which means I can replace the dx with du. And my integral becomes 7/5 integral 1 over 4 plus u squared. Now I just apply that formula that's over on the right hand side in the red bubble. It's just 1 over square root a. So in this case, our a is 4. Maybe I can write that down. Here we're using a equals 4. So it's 1 over square root 4 tan inverse u over square root 4. Square root 4 is just 2. Whoops. When I back substitute the u, I get 7 over 5 times a half, which is 7 over 10. Tan inverse x minus 3 over 2 plus a constant. So again, to recap what we're doing in this example, we've got a rational function with a constant in the numerator and a non-factorable quadratic in the denominator. So because there's no square root sign in the denominator, I'm probably going to try and make this look like the 1 over a plus x squared integral, the tan inverse integral. The way I do that is by completing the square. And then I may, in addition to that, also have to use the substitution, which we did here. We let u equals x minus 3, which is exactly the same idea we did in the part 2 examples. And then I just use my formula there and I get an arctan or tan inverse answer. Are there any questions on that example, on completing the square or any of that? Why we're doing that? We're going to do one more example, which is very similar to A. The only difference is that now we've got a square root sign in the denominator, which is fine. All that tells us is that the integral, the form of the integral we're trying to make this thing look like will probably be the arc sine integral. Okay, so again, any questions from part A before I go on to the second one here? But the process is the same. Okay, so let's go through this one in detail then, and that'll be it for the day. You have a constant, you have a function divided by a function, but the numerator is a constant, and you're recognizing the bottom as a square root. You've got this non-factorable quadratic under a square root sign. So you're going to have to use this strategy. You're going to have to complete the square of the denominator. So by that I mean you're just going to complete the square of what's under the square root sign. So on the right hand side we're completing the square. Rather than leaving it like that, I've written it in the reverse order. So I've written it as negative 5x squared minus 50x plus 1. And then I follow the same process I did earlier. I factor out, so I'm looking at, I'll highlight this again, look at the two terms here, factor out what's common. So negative 5 is common. Factor out negative 5, I get x squared plus 10x plus 1. Okay, now what do? I take, this is the important number right here, I take half of 10 and square it. So 1/2 of 10 equals 5. 5 squared is 25. I add and subtract 25 from the x squared plus 10x put some round brackets and then a set of square brackets, and leave the 1 outside hanging out there on the end. Then you write the x squared plus 10x plus 25 as x plus 5 squared. Okay, and then you still have that minus 25 inside the large square bracket. So to get it outside, I need to multiply that negative 25 by the negative 5 that's outside the square bracket. So negative 5 times negative 125, negative 5 times negative 25 is 125. And when I add 1 to it, I get 126. So I've completed the square, but now I'm writing it in the reverse order. So I'm writing it as 126 subtract 5 times x plus 5 squared. So now I replace my non-factorable quadratic in the question with what I got from completing the square. And while it doesn't look exactly like the integral I wrote there, you can see that now our integral has the same form. It looks like the integral of 1 over a squared minus bx squared. Okay, we can use the formula there. But first, I need to do a little substitution. I need to let u equal that x plus 5. Because if you look at our formula, it's just got an x squared. It doesn't have an x minus anything squared. So I let u equal x plus 5. From that, I end up getting that dx is equal to du. So my integral becomes 8 times the integral of 1 over root 126 minus 5u squared. And so again now, I'm using the formula from the lesson 2 days ago, or 2 lessons ago, 2 classes ago, which is this thing down here. It's the whole point of this example, is to make our question look like that integral. Our a is root 126, and the b is square root 5. So I just apply the formula now. I got 8 outside, so it's 1 over b, which is root 5, sine inverse b, which is root 5, over a, which is root 26, u, close the square bracket, plus a constant. And then I just multiply the 8 by 1 over root 5, and I sub back in my value of u, my expression for u, which is x plus 5. So a lot going on, I get it. You may have to review those examples a few times, but just try to understand big picture what it is you're doing. You're trying to make that integral look like the integral I've got in the bubble, which we know the formula for. It's just arc sine. Okay? And that's basically it for all the rules or strategies that we need for this course for evaluating integrals. I would say that these are probably the most involved. So, having said that, in addition to the 2 problems I assigned on long division, please try these 4 problems here where it says homework practice. So there are 3, the first 3 that are underneath each other. The idea there is you're going to be converting those by completing the square, converting those to look like the arctan. Notice there's no square root in the denominator. And the one over there, the multiple choice question, you can see that there's a square root in the denominator and a constant in the top. So you are going to be converting that to look like the arc sine integral. And that's it, folks. That's it for all the strategies of integration.